Good evening, everyone. My name is Alex Matrosov. So I will be talking about modern secure boot attacks by passing hardware root of trust from software. And I think actually firmware security topics, it's very important. And this year, theme of the conference, it's the matrix and imagine. So the firmware is the matrix and everything which is executed upper on the stack, like operating systems, it's inside the matrix. And if you have infection inside the firmware, everything can be faked. So it's why this topic is very important. And let's dig in. So I'm leading offensive security research at NVIDIA. And I do the firmware stuff already around like 7 years. And I have done a lot of research by passing before like a secure boot and talking about concepts, how basically the firmware rootkits and implants can be implemented and how it can be detected by forensic routines. So with my colleagues, Eugene Rodionov and Sergey Bratus, we write this book, which is actually have some cool stuff about the rootkits, bootkits, and firmware threats. And especially it's interesting because we create some concepts about how the forensics can work for that. But in the same time, I want to highlight the point, I don't speak my employee, and all opinions, information, and bad jokes, 0 days, it's on me, not on NVIDIA. Don't blame NVIDIA for that. For my research, I used my Lenovo laptop, Lenovo ThinkPad P50, which is pretty new and I like it, but also I have some security concerns on it. In my previous research, I mostly focused on Gigabyte, Asus, MSI, but you know what? They just don't care about the security in general. They even don't have security teams, and so basically they just broken. They don't have a proper secure boot setup. They don't have proper updates for the firmware and also integrity protection for the firmware update. So it's not interesting for me to focus on that because you always can find something to break everything. And Lenovo actually have a pretty good solid security, but some points I will be highlight today about their problems, especially on the secure boot and boot guard implementations. So we will be focused on what is actually hardware root of trust. And after that, we will be discuss boot guard bypass. And boot guard, it's technology for armoring secure boot on x86 Intel CPUs. And after that, we'll be focused on Computrace. And Computrace, it's kind of like anti-theft technology. Introduced a while ago and used in many laptop vendors, and not actually only laptop vendors. And let's say it's kind of legit rootkit inside your system and is activated. It provides a lot of opportunities and also have some vulnerabilities, which is have a possibility for the attacker. We'll be highlight some points on it. So other topics which I want to discuss is SMI handlers over Windows Management Interface. SMI handlers is kind of like a callback functions from the operating system level to the firmware, and we will be pointing some interesting stuff about the vulnerabilities and possible attack surface there. Embedded controller, it's also interesting place to look, and we will be discuss the topic why is not a security boundary. Okay. So what is the hardware root of trust? So basically, one of the main components for protecting your platform, it's baked inside the hardware, and usually hardware root of trust, it's kind of like a hash inside your CPU or inside some specific fuse. Let's say it's kind of like a small piece of memory to store the hash value, and it's locked. It's mean like it can be just burned on the factory once, and then you can basically change this value. But in the same time, it's lock the value which is used for integrity all the way for secure boot on upper levels. And actually supporting hardware root of trust for the platforms, it's kind of hard. Main problem with the hardware root of trust is because basically for main hardware vendors, you need to support it. You need to basically, if you have some damage on your laptop, I mean like some chip not working properly, you need debugging somehow. And all these things, it's hard to implement if you log everything. So you need to provide some support interfaces, debug interfaces, and basically ways to recover the platform. And it's really hard to make secure. And in following slides, I will discuss why. And in the most cases, it's also like root of trust. It can be just one bit value which is log something inside the hardware and pointing it's secure or not, or it's correct or not, true or false. So yeah, it's also like really hard to, really easy in some cases to bypass. And secure transition, imagine you have a secure boot which is start from the hardware and make a transition in the firmware on different boot stages. And this secure transition, it's hard to implement secure because imagine first you have a root of trust inside the hardware, then you check on the next level, which is already not on the hardware, so it's pure software. And it's a way for basically how the attacker can break it, because if it's just in software, it has some limitations, and we will also discuss that. I want to start actually with some classification of UEFI vulnerabilities. Here is a link on full blog post which I wrote recently, and with more information about that. But I want to split on the two big groups of vulnerabilities for UEFI firmware. First one, it's a result of exploitation, and second one, it's compromised supply chain. And supply chain, especially for modern hardware, it's really hard because think about, you have a laptop, but it's not all the chips developed by one vendor. It's multiple chips. As example, you have a Wi-Fi, you have a LAN Ethernet interface, you have multiple things, and in most cases, it's a different vendors develop these chips. That means it's also different firmware, and in many cases, the vendor who produced the laptop, they doesn't have access to this source code. So basically, they get a binary blobs from other vendors, and they not really control this source code. That means they just trust some integrity checks or signing of these binary blobs to integrate in their own hardware platforms. And also, in many cases, vendors can forget to log the configuration, some of the security features, and it's why basically we can have a weak configuration, one of the group on the right side, and also BIOS update issues when, as example, some of the things can be outdated after you buy the laptop. It will be not a recent BIOS version and on your laptop. That means it can be vulnerable for known issues. And in many cases, actually, how frequently you update your BIOS on your laptops? Many people just never, you know, like they buy a laptop, use it, but why I should? It works, right? So, but we'll be actually highlight some good stuff why you should update your BIOS. And second group, actually, it's a result of exploitation, and why actually secure boot bypass is important for the attacker, because think about if you can bypass a secure boot, your malicious code can be executed on early stages and then basically compromise everything upper. In modern days, it's actually not easy to break secure boot if you have a proper configured platform with all the new security features from Intel and other vendors, but the firmware actually is the place where the secure boot is set up, and if you get inside the system management mode, SMM, or have a privilege escalation to execute your code inside this mode, it's create actually a lot of possibilities for the attacker. And in some cases, it can open the door for bypass secure boot. But my main topic for today, to bypass the root of trust, baked in hardware. That means SMM issues will be not help here. So, and let's go actually a bit deeper and talk about how this hardware implementation for armoring secure boot works. So we have a CPU reset. What that means? It's just basically when CPU, almost just the first executed commands when CPU just started, it started loading the CPU microcode, which is stored on SPI flash. And after that, it's execute binary blob, name it as bootguard ACM. It's produced and signed by Intel. And ACM, it's authenticated code model. Basically, it's binary blob with some header and sign inside in the header. And this ACM, it's basically checks the integrity for all the other levels what should be executed after that. So after the reset vector, it executes IBB, its initial boot block. It's kind of like a also small piece of code with the hashes, which is check secure boot, or it's like integrity for other stages, Dixie, BDS, and the secure boot stage, it's actually mostly focused on OS loaders. Okay, looks perfect, right? Everything is secure, everything is checked, but think about if we have something broken inside the hardware, and in many cases, actually, for secure boot, TPM can be root of trust, and some researchers already present before a lot of stuff which is basically shows the problems with TPM, and if attacker can basically go inside or break or execute code inside the TPM firmware, nobody expect attack from this level. And with the physical access, you can do it, right? So you can just fake the TPM and try to attack some of the code executed on the firmware level. And Jeremy Boone from NCC group actually shows a lot of issues with this kind of attacks. And here is a GitHub of his research, and I highly recommend read this article. It's very interesting. So, and in the perfect world, also we have microcode or ACMs, authenticated code models, authenticated by something. I mean, like it should have some code or security checks which will be check the integrity for that, but we're not in the perfect world, and this code is actually never checked for the integrity. Of course, it's signed. I mean, it's after it's loading, it's checked by CPU, but thing is, you can basically downgrade the microcode, which is interesting, especially for speculative execution and all this stuff. You can just downgrade, and all these speculative barriers will be gone, which is kind of interesting. And I would say microcode in many cases can be like also name it as a hardware root of trust, because it's executed inside the CPU, which is basically very different with any other firmware, but it's also like a firmware. So let's back to the bootguard. So how the boot flow in the real world looks like. So we have a locked-in hardware CPU microcode, bootguard ACM, and after that, we have actually everything else. But if ACM can be downgraded and microcode can be downgraded, that means we can use the one-day issues to basically bypass all other levels. In my previous research in Black Hat 2017, I've been presenting some stuff when I've been diff multiple bootguard ACMs from the different platforms and highlight the issues there, just like, which it's easy to find, but not easy to exploit. So why don't lock everything inside the hardware? So hardware is not flexible, and it's very expensive to support. IAMs don't like locking secrets inside the hardware because it's basically increase the price for support. And in many cases, the laptops have like a 5-year support from the vendor, and Apple actually have even more. all the vendors try to reduce the hardware locked secrets because it's also this flexibility in firmware. It's create a lot of things when you can extend and more open for flexibility with the third-party components or like chipset, firmware's communications, or everything else. And when basically the main vendor doesn't control that, but the interfaces can be changed, and if it will be locked inside the hardware, how basically you can fix it. So it's hard. And I highly recommend to look on this talk from Positive Technologies, which has been presented recently on the Black Hat Asia a few weeks ago. And it's actually, I just make a copy of their slide about supply chain, and you can see how many different points for supply chain just for basically deliver the firmware on your laptop involved. So any point of compromise for these different points basically cause security problems, really serious security issues. So how basically we can bypass Intel boot guard? So yeah, I already showed twice different ways how bypass the boot guard on Black Hat, and oops, I did it again. And what is actually a root cause of the problem? Recovery mode is evil. What does that mean? Basically, when the vendors try to create some alternative path to recover the firmware, or basically to manufacturing mode for support, it creates security problems in many cases. Secure transition chain of trust is a different boot stages involved, so it's hard to make it secure because basically after secrets leave hardware root of trust and go to the software, it's much easier to bypass. In most of the cases, without hard reset, root of the trust just move to the pure software. And I will be actually described why. Think about when you close the lid of your laptop and open, how many milliseconds passed between the screen blinked. And if it will be basically go all the way down and verify all the stages from the scratch, it will be taking minutes. And of course, who will be buy this laptop, right? Why you should wait a few minutes just to basically make your laptop works? Nobody will be buy this kind of stuff. And vendors, of course, very focused how make it work faster. But it creates security problems because you start from some point when it's already passed a lot of stages, and if you just verify your root of trust there, and if somehow the attacker can execute the code on the same level, it can be bypassed. And in many cases also, Intel introduced technologies Intel BIOS Guard, and in many cases it's just don't used or not configured properly, and I've seen this on many vendors, but I think it's good point for my next talk. And also I want to discuss some of the real issue from recovery mode actually with Intel NUC platforms. It's been discovered by Alex Yermolov, researcher who presented this stuff on Zero Nights last year. And it's problem exactly about basically leaving root of trust from hardware to software. And when update software have a lot of much more power than it's need, and basically it can override any region on SPI flash without authentication, and it's been a problem before. And yeah, I will make it bigger to visible. So basically the hash verified in pure software, and it just compare hash which is also not read it from fuse, it's already exists on the NVRAM. And just a mem copy of these two values, and of course it can be ignored in some cases when it starts recovery, and it was issue this one. So yep, thanks for pointing my research to Alex Yermolov. You can see this blog post about basically issues with update tools on my blog post, on my blog. Okay, in this issue, it was basically root of cause of the problem bootguard pay, which is kind of like one of the pre-configuration before Dixie stage, which is just the last one before goes to bootloaders for the operating system. Yeah, and let's back to the bootguard. So actually, it's how it looks like. We do have basically a management engine, which is read-write fuse, but after it's write the fuse, usually during the manufacturing, it should locked. That means it will be never overwritten anyway. So it's a root of trust. We do have some chain of trust inside the firmware. We do have a K manifest, which is a root of trust inside the firmware, depended by the fuse value. And it's actually integrity check for the fuse value, for root of public key inside the K manifest. And initial bootlock manifest, which is basically dependent by UEFI firmware image. But think about, if we don't have this point, everything is just locked inside the firmware. And it's exactly what I talking about before. It's create possibility, break everything is inside the firmware. So, and it's a picture when how it's actually research been started. I've been seeing this picture on some of the updates on my system. And okay, interesting. It's disabling the bootguard from software. How it's possible? Because it's basically should be locked and disabling the bootguard need run the setup with a password, and only that can cause the disabling, but it's running from the operating system level and somehow disabling the bootguard. So, okay, I should basically dig in and try to understand how this works. And I was go to Lenovo OPCDE platform configuration init driver and look inside this call. And okay, it's wow, it's interesting how this basically connected to the disabling of the bootguard. And then I found this check. It's basically reconstructed code from disassembly, and it checks the PCD, platform configuration mode, is active, and then it's basically disabling the bootguard for Dixie stage verification. So what basically happens, it's disable all section of the drivers, which is executing and communicating with the operating system just before pass-it control from platform initialization mode. And I was also think about, okay, they need to store this value somehow in bitmap inside the firmware image. And I found this padding, this one, which was not covered by bootguard, and it stores some weird bitmap. Here it is. And I was playing with different values around these ones. And actually, if you make it now and reboot your system 3 times, it's disabling the Dixie stage. But first time I've been confused because I changed the value and nothing happens. I was okay, but code says it can disable, but what is not doesn't work. So I started experimenting and just like sometime accidentally I reboot few times and then it works. So yeah, don't blame me if you try to reproduce. Just make more resets on your system. So also I was looking on the spy dump flash, and here we can see the difference. So basically this padding and it's this padding inside spy flash dump. So it's original BIOS update and with a dump. So you can see it's highlighted now. What is the difference? It's actually here. So you can see it's basically have a more configuration data from the manufacturer. But I don't know what is basically all of these bits, but yeah, I just discussed one which I already experimented and play around. So why vendors leave this kind of like backdoors? It's not a real backdoor. They create the way how they can debug or basically recover the platforms. But from the attacker perspective, it's really like open the doors to install or like implant on your system, because it's no validation on the secure boot stage, right? So, but for vendor, like I mentioned, it's a lot of things, because enterprise market, it needs stable solutions, right? And if it's not, you need way to debug it. So also, somehow you need way to recover your broken firmware. So it's also a possible way why they create this kind of possibility. So it's a lot of open questions, but interesting fighting. Let's move to system SMI handlers over Windows management interface and why it's evil. So let's talk a bit about how you can exploit the system firmware. And it's actually a path from the operating system level, and you can see how many exploitation exploits you need. It's around different 5 chain it in one exploits, and the most interesting one, when you basically elevate the privileges to system management mode and try to basically get the spy flash rights from this level, because it should be isolated on any others, but some some BIOS update tools have some evil possibilities, but not all of them. Okay, so I started looking around how many things located inside the SCPI tables and how many configuration data stored there. So yeah, you remember this screen, right? So, and Lenovo actually on their website says in documentation they do have interface to call SMI handler, and as I mentioned, SMI handler, it's callback function from the firmware to the operating system level over Windows management interface. On the previous pictures, actually, I show you need escalate the privileges from the user mode to the ring 0 to call the SMI handler. In this case, you just need a root on the platform or like system privileges to call Windows management interface, and that's it. In many cases, you just need administrator, even like you don't need system, right? So, and it's how many different configuration values stored and can be controlled by this interface. And I will show you a bigger picture with most interesting ones. So you can see like it's possible to disable TXT, trusted execution feature for your hardware. It's like disable or enable rollback protection. Also, it can be disable, enable for secure boot. Yeah, it's a lot of stuff, and it's kind of like scary, right? VTD, especially for like creating DMA barriers for DMA attacks, also can be enabled, disabled here. So how you can find this interface? So I use a read-write everything tool and open the tab with a specific SCPI table DSDT. Yeah, just you can see if you just basically try to find VMI, you can just find different possibilities to call this interface. So here is an example of Visual Basic script to basically update administrator password for your firmware from the operating system. And this script I just copy-paste from Lenovo website. They're really nice to create this example. It shows like really a lot of possibilities from Windows management interface. So welcome to brave new world. And yeah, so I was thinking, okay, we do have Windows management interface, and also we have a remote configuration, drivers, and Lenovo setup automation. It should be connected somehow, and it is. So basically, these two drivers, it's implementing this interface for the operating system level. And here is some description what is implemented on different drivers described on the previous slide. But for me, it was most interesting one, Lenovo hidden setting. What is it? So it can disable and enable CPU debug and also Computrace. And as I mentioned before, Computrace is kind of legit rootkit to track anti-theft your laptop as an anti-theft feature, and it's basically have a permanent disable option, but yeah, let's talk a bit later about that. So setup Automation SMI, it's a numbers, and it's like over 15 of SMI handlers involved, and it's like a huge attack surface because it's actually have some they ignore some of the security checks which they used on the other drivers, which is like, okay, probably old interface forgotten by the developers. But let's now switch to Computrace and why it's interesting. So I don't know you remember or not, but in the end of the last year, ESET antivirus company been discover interesting rootkit based on Computrace, name it like a LowJax. They released a report. I will not dig in the details of this rootkit specifically, but I will be dig on Computrace, which is used as an implementation feature for that. So my main concern, so okay, Lenovo remote configuration is connected to Windows management interface. So you can do it something remote. And I was tweeting about that, and a lot of people like this topic. I decided to reconstruct some more information about that. It's slide from my previous research you can find on this link. So basically, I was talking, okay, Computrace can be disabled permanently. It's a setup menu from my P50 laptop, and I was thinking, okay, probably they use a fuse, but not really. They just use 1-bit value inside the Lenovo hidden setting and Lenovo security config. And no permanently disabling for Computrace on your laptop. So really, all these drivers just executing and do nothing. And if the attacker can get to system management mode or like probably patch it, these drivers, even with permanent disable, it's still executing, so it can be reused. So why it's so dangerous? It's architecture of how different Lenovo security features and Lenovo Computrace SMI services connected. So we have a Lenovo hidden setting, Lenovo security config, and we do have few components like Lenovo Security SMI Dispatcher and Lenovo Mailbox. And let's look how it's basically connected. But before we dig there, let's check what is the fields. I recovered some of the fields by reverse engineering Lenovo security configs from different platforms. So, and we can see here, like, it's a lot of stuff. So, and it's also tied to what we've been extracting from operating system level. You can see secure boot, TXT. So basically, it's tied to there. And even device guard, it's Microsoft feature, it's also there, which is interesting, but I'm not surprised because basically device guard need to understand its hardware is support this feature to enable this feature on the operating system level. And basically, it's also like just true or false in configuration for Lenovo security config. But let's talk about Lenovo SMI services. So I was thinking we do have some SMI handlers which is used inside the Computrace, but what this SMI handler does, So it's in numbers, and as you can see, it's enable, disable, state. Basically, it's enabled or disabled. If you call this Computrace state, it will be return the status. And enable action and disable action, it's basically ones which can be called from the operating system level. So yeah, it's kind of like, why too much SMI handlers involved for this simple feature? And why it's too much possibilities activated differently. So let's look on Lenovo Scratch data, because it's one which provides a state of Lenovo Computrace, and this one on the right side, it's recovered from NVRAM, and it's like how it's configured. Basically, it's a bitmap, right? So basically, can check how Lenovo security config looks like inside also NVRAM. Yeah, and it's also bitmaps, just like 0, 1, if it's need to be active or not, which is easy to attack. But I was mostly thinking how the disabling and permanent disabling works. And the flow is quite complex, so I summarize it with this pseudocode, how this algorithm works. And you can see, so if security config Computrace is true, basically it's enabled. If it's something else, then it's disabled, which is quite simple and also don't look like a permanent disable, right? So here is a SMI Computrace enable flow, how it's worked. And also, I was thinking, okay, here it looks much more interesting because we need some value inside the AX register, which is basically will be flag something. And digging deeper, so it is Computrace state, which is have a value disable secret key. I was, okay, here's game over, because it's like a 4 bytes key, like how we can brute force it, right? So it's difficult. But then I looked how this key is verified inside the firmware, and it was funny, because it's symmetric algorithm used here for derivation of this key, and it's depend by just 1 byte symmetrically. What does this mean? You can brute force 1 byte value, and other 3 bytes will be just derived by this function. And that's, wow, cool. 1 byte, it's really fast to brute force and make some automation for my penetration testing tool. So, and other roadblock was, okay, so if they do constant time comparison for this byte, even with 1 byte, it can be a bit longer, but they failed even here because it's not constant time. And brute force, it's less than 1 minute, actually. So here is a small script with a chipsec tool. When you call a specific SMI handler and try just brute force 1 byte value, so it's fast. So I get, I don't know, probably in 20 seconds, 0x57 for my P50 laptop. And in some cases, different Lenovo lines or different Lenovo ThinkPad series can have a different disable key. So my key for Lenovo P50 and my key for Lenovo P540 was a different. So it's not basically surprise, but it's still 1 byte. So it's main concerns about Computrace, and also one of them is Lenovo used always the same version of Computrace. It's been basically not updated more than 5 years. Probably they license it some, but after that they not update the license because they don't have new license for newer version or whatever. They just keep using the old one, which is like full of bugs. Embedded controller. So embedded controller, basically it's small chip based usually on Lenovo ThinkPad. It's based on ARC CPU, and it's in the past it's been just like a keyboard controller and used for some of the restore features for sleep mode, but for power actually. And but for nowadays it's much more. It's have some security features based on embedded controller, and probably it will be my talk for the next Black Hat, but let's a bit check how the embedded controller looks like. So this one specifically, you can see it have a connection to DMA lines and have access to PCIe devices. So basically, nobody thinks from the platform vendors on embedded controller as one which is can basically attack embedded controller, its security boundary. So, but if it's updating separately from the main firmware, that's mean, or sometimes it can be the same update container. But anyway, so if you can bypass authentication for the firmware on embedded controller, you can basically attack the main firmware or attack some devices which is accessible over PCIe. And most of the platform vendors don't include this attack vector on the attack surface. And this one, I will not tell the name of the vendor, but you can see it's no authentication. It's just, it's the update routine, and it's just flash it. And it's very nice comments, actually. I not put myself. All the developers do better than me, so they put all the comments, which is much easier to read this decompiled flow. Okay, so let's do some summary for my talk. And I think the usability in enterprise world, in many cases, it's main enemy of security, and we need to find some balances here. The vendors can understand permanent disable option differently. It's a lesson learned with the Computrace, and when the hardware-based root of trust transfers the state of chain of trust to the software, it's not already hardware anymore, right? So it's pure software. Thank you very much for your attention. I hope you enjoyed the talk. Thanks, everyone.